In this demonstration, we examine the effect of salt water on ice melt, with an eye toward melting of ice sheets and sea ice on the world's oceans. I have made artificial icebergs from crushed ice, cemented together with a little water and refrozen, equalized the water in the beakers containing fresh and salt water, then added dye to the tops of the ice balls. My camera's battery gave out after about 15 minutes, and I discover it after half an hour. The first 15 minutes will be compressed, and I will resume normal speed after 1/2 hour has elapsed. The iceberg in the freshwater side, on the left side, has almost completely melted now. And on the saltwater side, the iceberg is about the same diameter, or a little bit less, but it hasn't melted very much. Notice the height of the water has not changed at all. So even though ice sticks out above the water line, that weight is displaced by the water itself. So as the ice melts, the amount of water that is actually in there does not change. At the top, or at the bottom of the freshwater tank, it's about 7.2 degrees Celsius. And at the top, near what's left of the iceberg, it's about 8.3 degrees Celsius. In the saltwater tank, at the bottom, it's 13.2 degrees Celsius. Remember, it started at 17. At the top, in the middle of the yellow layer, it's 9.0 degrees Celsius. Now, why could this be? Why is it warmer at the bottom of the saltwater beaker and colder at the top? Usually cold water settles to the bottom, but in this case it doesn't. The reason that it doesn't is because the cold water on top is fresh water and it's less dense. Even though it is colder, it is less dense than the salt water below it, so it floats on top. This is an important thing to note because as icebergs and as the ice caps are melting, the fresh water will stay on top rather than mixing with the salt water down below, and it will cap it and possibly change the flow of the thermohaline circulation.